Hello, in the last videos we discussed about bind search. Let's discuss some problems. You are given an array nums of positive integers. You are given another integer array queries of size m. For each query you want to make all elements of nums equal to queries of I. You can perform the following operation any number of times. Increase or decrease any element by once. Return an array of size m where answer of I is minimum number of operations to make all elements equal to queries of I. Note that after each query the array is reset to its original state. Values of n and m can go up to 105 and the values can go up to 109. For example, if the array is 3168, if we are trying to make all elements 1, the number of operations required are 3 minus 1 to decrease 3 by twice and 1 minus 1 because there are no operations required, and 6 minus 1, 8 minus 1. So it will be 2 plus 5 plus 7, it will be 14. And if we are trying to make all values 5, the operations will be 3 minus 5 because we have to add 2, so it will be 2. And 1 minus 5, 6 minus 5, 8 minus 5. So we can just rearrange to get a positive value. So finally will be 4 plus 2 plus 1 plus 3 which is 10. So we have to return answer vector new vector of size m where every value is the number of operations required to make all elements to the given value, which is query of I. So if the values are greater than or equal to x, then answer will be simply vj minus x, because for example if the value is 5 and we are trying to make the value 8. For example, if the value is greater than or equal to x. So for example, if this is x and this is the y, so what are the decrement operations required? It will be y minus x, because it will be vi minus x when vi greater than or equal to x. When x is greater than this, for example, we are trying to make 3 6, so we have to add it. So now the value will be x minus v of j. So if the value of v of j is greater than or equal to x, it will be v of j minus x. And if v of j is less than or equal to x, then the operations required are x minus vj. So if it is less than x, it will be x minus vj. And if it is greater than or equal to x, the answer will be vj minus x. So for all numbers which are greater than or equal to x, the answer will be, let's assume that all elements are greater than or equal to x in the whole array. So answer will be v0 minus x, v1 minus x, and so on. So now the value will be sum of all values minus x into count, because we are decrementing x and count is the number of elements initially in the array. And now if all elements are less than x, now let's assume that all elements are less than x. So then what will be the answer? It will be x minus v0, x minus v1, and so on, which will be equal to x into count minus sum, because we are decrementing v of 0 from x, so it will be x into count minus sum of all. But initial vector can contain elements which are equal to x or greater or less than x. So how to differentiate this? So simply we can sort the vector and we can separate all elements which are less than x and greater than or equal to x by lower bound, because lower bound returns the first index which is greater than or equal to x. So from that index all elements will be to the right side are greater than or equal to x, and all elements below it are less than x. So second operation can be applied here and first operation can be applied here. So in this way we can use sort and use lower bound to find smallest index greater than or equal to x. So count 2 into x minus sum of before, because all before elements are less than x, so it will be x into count minus sum of all. It will be sum of minus sum of before, and sum of after minus count 1 into x, where count 1 is the number of elements which are greater than or equal to x, and it is number of elements less than x. So now we have got a of an approach for each query, because we have to find the sum of before and sum of after and the size for each query to make. But the query size is 10 power 5 and the size is also 105. So we have to optimize each query to of 1 so that we can get answers in of 1 for q of 5, for q which are 10 power 5. So for example, let's observe that this is query 1 and this is query 2. So for example, let's say the lower bound 1 returns this and lower bound returns this. So what we want from this? We want sum of all elements before and sum of all elements after it. So we want this whole sum, because these are the elements which are greater than equal to x, and we want sum of this, and we want the sum of elements which are lower than equal to x as well in this query. Similarly, if the lower bound is, we want this and this sum as well. So if we observe carefully, at every operation we want only some prefix sum or some suffix sum. Maybe that index may be varied, but the operation we always want is to get sum of some any prefix or query or suffix in of 1. So simply we can use prefix and suffix sum so that we can find any prefix sum in O of 1. So for example, if the initial values are 1, 2, 6, 7, 7, 8, it will be 1, now it will be 3, it will be 3 plus 6 and so on. So if we want any prefix operation which is sum, we can get an off one. So in this way, if we just try to pre-compute prediction suffix sums for every query, we can find the lower bound and we can get the whole sum which are right to it by suffix sum of lower bound, and then we can use count and we can find the answer. Let's check the code. We are initially sorting the vector and we are making prefix sum and suffix sum. PS of 0 is equal to f0 and suffix of last limit is equal to last limit. And now we are traversing from 1 to n and PS of j is equal to PS of j minus 1 plus v of j. So we are adding the before sum with present element and storing in PS of j. And similarly suffix sum. And now we are traversing all the queries and finding the lower bound of q of j in the vector given. So if the lower bound of 0, it means that all elements are greater than or equal to x. So for whole elements, the first operation will be satisfied and it will be suffix sum of 0. So suffix sum of 0 or prefix sum of n minus 1 are same, which is equal to sum of all elements. So now the answer will be total sum minus n into q, because all elements are greater than or equal to x, so it will be n into q of j, which is the query. And in similarly, if LB is equal to n, it means that all elements are less than x, because there are no elements which are greater than or equal to x. So for all elements, the second operation is satisfied and it will be count into q minus ps of n minus 1. Similarly, which is sum of all elements. And if it is not 0 or not equal to n, it is some middle operation, it is some middle index, and we want to use both. So it will be suffix sum of LB minus number of elements after it plus count into q of j minus ps of LB minus 1. So in this way we can find operations, each query operation of 1, and we can return the answer. Now let's discuss another sum. You are given two positive integers nums1 and nums2 both of length n. The absolute sum difference is defined as sum of mod numsi minus nums2i for all indices 0 to n. You can replace at most one element of numsi with any other element in numsi to minimize the absolute sum difference. Return the minimum sum difference after replacing at most one element in there in nums1. Since the answer can be very large, we return it modulo 1 in n plus 7. For example, if the values are 175 and 235. So if we try to replace second element with the first, so the new array will be 115, and if the new array is 115, the sum difference will be 2 minus 1 plus 3 minus 1 plus 5 minus 5, which will be 3. And similarly, we can replace second with third as well, and then the new array will be 155, but the difference will be same, which is 1 plus 2 plus 0, which is 3. So in this way, we can replace any one element with any other element in nums1 to get the least sum of differences of indices. The values sizes can go up to 25 and the values can go also up to 25. So let's say this is the first array and this is the second array, and now we are, because we have operation only, that we can replace any element in v of I with any other element. So we can start traversing, and at every index we have to replace vi with such a number that difference between that and v2i is least, because we want the least sum. So if we are at index 0, what we want the least difference that is satisfiable from this. So we can find the least difference that is possible with respect to all elements from v1, so that the difference will be least due to v2 of 0. So, and initially we are storing the differences in v, in the vector v, so that we can get the differences in of 1. So we are storing, and count is the initial answer. So without doing any operation, the answer will be count plus modulus of difference of both, and we are doing mod m. So initially, without doing any operations, we are storing the differences of all indices in v, and initially the count answer is count. And finally, the goal reduced to find the value in v1 such that it is closest to v2 of j, and we traverse j from 0 to n, so that we are traversing all elements of v2 and finding the most nearest element and replacing that to get the least difference. So for example, let's say this is the first vector and we want the least difference when the number is 3. So we can sort it because we just want the differences, so it is enough to sort, because we don't need to return any indices such like that. So we can sort it and we can get the least element that have minimum difference. So in this way we have directly 3. So the differences will be 2, 1, 0, 0, 1. So 3 minus 1, 3 minus 2, 3 minus 0, and 3 minus 4. So the differences will be 2, 1, 0, 0, 1. So the least difference is 0. So if we observe the graph, it is decreasing and increasing, because it is 2 initially, 1, and it is 0 and initial. And similarly, if the value is 5, we are searching to get the least difference, and the values are this 1, 2, 3, 4, 4, 7. The new difference will be 4, 3, 2, 1, 1, 2. And similarly now it is decreasing and increasing as well. And if it is 1 on 5 which is initially sorted and we are trying to find for 4, so now the difference will be 331 and similarly which is decreasing. So if we observe one thing, when we are trying to get the different least difference that is possible with x, for the highest element it is highest and gradually it is decreasing and it is increasing. So at what value it is decreasing? Obviously the closest elements with respect to x have least difference, because if I have 3 and if I have 2 and 4 which are more closest, and if I have 10 and if I have minus 10, so obviously the values will be least for 2 and 4 because they are very near. So obviously we want the elements which are closest so that we can get least possible difference. So how to get this? So even now we want element greater than equal to x, because that is the least element that is greater than equal to x, because all elements right to will be greater than x and all elements before less than x. We have observed that the even the value will be least when it is greater than equal to x for the least value. So we want greater than equal to x. So even now we want lower bound. So after getting the lower bound, is it sufficient to check only for the difference between lower bound and the present value? No. We have to check for the present value and the previous one. Why? Let's take for example the vector is 4589 and the value we are searching for is 8. So the lower bound returns this because 8 is already present. So the answer will be 0 because 8 is directly there. And now coming to next case, we have 4, 5, 9 and 10 and we have the value 8. So the lower bound returns 9, right? So all values before it will be less than 8 and all will be greater than equal to 9, greater than equal to 8. So the difference between 9 and 8 is 1, and the difference between any element greater than 9 and 8 will be surely greater than 1, because this is the least element which is greater than equal to x. So after all elements, obviously the sum is going to increase and the difference is also going to increase. So there is no need to check for the lower bound next one, because it will be surely greater than x and the difference will be surely greater than lower bound. So it is waste to check all the next ones, and we have to check lower bound and we have to check the previous as well. For example, if the value is 139, there is 139 and the value we are searching for is 4. So lower bound returns 9, but the previous value is 3. So obviously the difference between 3 and 4 is 1 and 9 and 4 is 5. So answer will be 1 because we have 3 which is less than 4 with the least difference possible. So for every element x we can find the least difference value which will be lower bound and the present value, or the element below lower bound, before lower bound and the present value. So from this we got an idea that we can traverse whole v2 vector, and for every v2 element we can get the least difference possible. And now we want the minimum sum possible. So we want maximum difference from initial difference and new value, because we stored the initial values in v when we are doing no operations. We have got a new difference vector where it is the least difference possible when we are trying to replace ith element to get the least difference with respect to v2 of I. So we want the least difference and we want the maximum difference from initial to get the least value, because initially the value is 10, the difference at some index I is 10, and after replacing it is 1, and for other index it is 3 initially and it is 2. Obviously it is beneficial to choose this one because we are having the most decrement. So the answer will be affected more, which will be decreased. So we want the maximum difference, so we are traversing finally. V of I is the initial difference at index I, and V1 of I is the most optimal difference that we are able to get when we are replacing V1 of I, nums1 of I with value that will give least difference with nums2 of I. So it will be maximum of all. And finally we are written count is the minimum initial value, and we are reducing the value by 9, so it will be minus answer plus m. But why plus m? Because a minus b mod m is equal to a mod m minus b mod m plus m whole mod m. Because for example, if a2 b is 4, 2 minus 4 mod 3, it can be simply written as 2 minus 4 plus 3. So that value is always positive, which is 1. So it is just a care that even if count is less than answer, answer will be obviously positive because we're adding game. So let's take the code. Initially we are maintaining two vectors v and v1. V is for the original difference without doing any operation, and count is the initial value, initial answer, and we are sorting it, and we are traversing the second vector and finding the lower bound of nums2 of I in the first vector. And if it is 0, it means that there is no need to check before element because the lower bound is 0 itself. So v1 will be obviously the difference between present element and the nums2 of I. And if pos is equal to n, it means that lower bound is n. So it means that all elements are less than or equal to x. So obviously we have to check with the previous element. So v1 dot pushback pos minus 1, which is the last element. And if it is not both, it means that there is some middle index, and we have to check both lower bound and before value. So we are pushing the minimum difference. So we will not push back absolute value of present value and lower bound, present value and lower bound before index. So we are showing this in V1, and finally we are traversing the loop again, and finally the maximum difference. And finally we are returning the answer. So hope you understand this. If you have any doubts, comment below. Drop a like. See you in the next video.